So I'm from ICFO, and for the people that don't know, we are south of Barcelona institute that is mostly focused on photonics and optoelectronics and quantum photonics. We're very close to the beach. That's important for the well-being of the students, especially in COVID time. I will come back to that topic. But first, I want to motivate. And the title slide I actually skipped, but I'm going to talk obviously about cryosnom. And we are applying this to twisted two-dimensional materials. And this analogy with quantum simulation is not something that I came up with, but this was a picture that Pablo Grillo presented. Sorry, this animation stopped. Okay, so this is the animation of twisted materials. I think everybody has seen by now that this can create these beautiful moiré patterns. But what you really can think of is that this is a quantum simulation platform. And it is basically sitting in between two extremes. On one extreme, we have real quantum materials. And there, the scale of the lattice is on the order of a few angstrom. And that's also the scale, you know, on which electrons feel the presence of the atoms. And on the other extreme, we have cold atoms that are very nice simulation platform, but the length scales are much larger. They are on the order of a micron, and because length scales are larger, energy scales are smaller, and they have to go to very low temperature in order to observe quantum mechanical effects. They go to nanokelvins. Now, somewhere in between is moiré quantum matter, where also correlated effects can appear, similar to what happens in quantum materials like superconductivity and Chern insulator states, topology, etc. But this in the moiré quantum matter, you have much larger length scales on typical scale of 10 nanometers. So the length scale, and I will show the animation again. So the electrons basically feel this moiré superlattice. They are quasi-confined inside this moiré. And that's on length scales of 10 nanometers. Now, a while ago, in the cold atom lattices, they developed what they call a quantum gas microscope, where they could look at the individual motion of the atoms in such an optical lattice. And this really made many breakthroughs in quantum simulations. But the way I see it is that the moiré quantum matter is also a quantum simulation platform because you have tunability, you can change the size of the lattice, you can play with the interlayer coupling between the layers, you can apply electric fields. But what was missing is basically a way to image this. And this is what I believe we can do with cryo near-field microscopy, is to really probe this system at the scale of the moiré unit cell. And it's 10 nanometers or 20 nanometers, so it will be challenging, but I do believe that we're going to get there. And then we are able to probe lots of phenomena in real space, like superconductivity, topology, but also collective excitations. And something that I will also show you is that we can probe other properties, like the Seebeck effect, which is a photothermoelectric effect. And this is effectively probing the entropy of the system. So there are a lot of parameters you can probe. Of course, you need cryogenic temperatures. So we're building this type of platform. I actually want to advertise here that we're building also a joint laboratory on this topic together with Pablo Grillo from MIT, who is having a distinguished invited professor at ICFO, and there's also several postdoc positions available. So if you're interested, let me know. So, cryosnom. Is Colette somewhere here? I don't know if I see it. There he is. Okay, so he probably remembers this picture. He slept only 2 hours. This was a picture that we took just before the flight. So they installed the cryosnom in October 2019. There is the entire team. You can see we're all smiling because it was working. And here's Colette. And this is the cryosnom system. it's quite compact. The cryo head is down here. And here is actually the chamber, which you cannot see in this picture, and all the optics is in here, and this is the light source. And actually on the left side here, you see the other SNOM we have together with the terahertz gas laser. So everybody was very happy, the system was working. This was in October 2019. This is a better picture from close by. Actually, my favorite part of the system is the lighting, because this looks very mysterious here on the back, this white light. You can remember this Google quantum computer, you know, this 50-qubit quantum computer, always these images in the media as this very mysterious type of system, and this makes me also think of it. So I like that lighting. So, but what is something that we added later on is these active damping systems. These are very big blocks, basically, and then with active damping we can reduce the vibrations that come from our floor. And in particular in our building, we have a lot of vibrations coming from the air conditioning system, and this helped a lot. So this is something that is probably also interesting for some of you. Now, I also learned that the system has improved a lot, and I've seen the upgrade actually today already. Tomorrow, everybody should go have a look, and it's even better than it already was. But back in 2019, this is an image that we took on boron nitride. So these are phonon polaritons in boron nitride taken at 10 Kelvin. And so this looks pretty good. The signal to noise is actually very high. The number of fringes you see is very big. And yeah, so this is back in 2019. Then we wanted to really start working, and then this happened. So we got this email from the safety department. Okay, there is COVID. Try to wear masks. Then it said try to be with less people in the building. And then it's like you have to stay home. Okay, and I was like, okay, that's nice. I can go surfing, but also no, we had to stay home, really at home. So you could not even leave your house. Then slowly the lab started to open again, and we were allowed to go in the lab, but we're not allowed to meet together in one room, which is also quite depressing, so you cannot talk to each other. But we had a solution for that. So this is a picture of our group meetings in COVID time. So we would go to the beach, and that's outdoors, so you can meet with as many people as you want. So and that's where we did the group meeting. So he's actually giving a group meeting talk. You can see here a little bit the slides. There's some food, and this is a piña colada. This is important. The presenter has a piña colada. Now, what we use a lot is, with the cryo system, is the photocurrent nanoscopy, and that's what I'm going to show you the data, if there's time actually. And this nanoscopy, photocurrent nanoscopy is really based on the Seebeck effect. And a Seebeck effect is basically the effect of a thermal gradient that creates an electric field, and the strength of that is then governed by the Seebeck coefficient. And then this electric field can generate a current, and that's this integral. Now in reality, this is more complex, right? Because you locally heat up with a tip, and then you measure globally a current, right? So it looks like this picture. And there's lots of field lines and stuff, so you can wonder like, oh, this is actually difficult to calculate, because at each spot, you need to calculate the field lines and then the global response to the system. And some of these field lines actually make circles and etc. Now, thanks to Mark Lundeberg, who was a postdoc in my group, this has been worked out in high level of detail, and this is based on the reciprocity theorem, where you can actually take the inverse. So you basically say, oh, I have a current path from source to drain. I calculate the flow of all the current, and you take the gradient of these field lines, and then from that you can actually derive a photocurrent map. So this is now a way we analyze our data, and if you want to know more about this, it's on the archive, which is my favorite high-impact journal. The paper will never be published in anything else, so you find it on the archive forever. It's for free, and it's open access. So a while ago, we used that to show different things, domain wall boundaries. It was also used to image terahertz polaritons, etc. Now we're going to apply this to twisted graphene. And look at initially at structural effects like the moiré, but we want to also look at interaction effects, right? Because this is what twisted graphene has been excited for. So when you twist graphene at something that's called the magic angle, this is what happens at 1.1 degree. You get flat bands in the band structure. In Fourier transform, this actually means it's spatially localized, so you start to spatially localize electrons in this moiré superlattice, and then you reduce basically kinetic energy, and that means that the Coulomb energy becomes more important. Now, thanks to the work from Pablo Guerrero and other colleagues later on, they observed lots of interesting effects, and they could, as a function of doping, observe different phase transitions, such as the Mott insulating state and superconductivity. The way they interpreted this is that the phase diagram resembles high TC superconductivity. This is still under debate, but it has a lot of similar physical features. The way just you have to think about this is this. I see this as an egg basket. So the moiré is like an egg basket. You put electrons in each of these pockets. And then we speak about filling. So when you fill up each of these pockets, let's assume now with 1 electron. In the practice, it means 4 electrons because we have spin and valley. But OK, let's just say filling 1. Then it's a full filling. Then you get a gap. An insulating state, but also if you have half filling, that's here, you get the Mott insulating state. This is a pure interaction effect. Then if you dope it a little bit more, compared to half filling, becomes superconducting, and nobody knows why, but that's exactly why it's interesting and why it's called a quantum simulator. A lot of other things have been seen. I will skip that. But we're probing this system with light. Why? Because if you look at the band structure, you can actually see there are many infrared transitions that move from the flat band to the remote band, which is also quasi-flat. So you have 2 peaks in the density of states with strong optical transitions. Initially, we were probing collective excitations. These are images of interband plasmons. I will not go in detail. Then it was possible also to look into the moiré unit cell. And here you see photocurrent images of the moiré unit cell. This is a sample where the twist angle is varying a lot. So you can see different sizes of the moiré unit cell. Pablo is actually already cutting me off, and I still have to get to the beef of the talk. And this is the technical problems, technical problems. So this is... this is what's really doing at cryogenic temperatures. So I showed you this band structure, but if you now, as a function of filling, okay, so that means I add electrons in this egg basket. If you look at the Seebeck effect, it shows peaks at full filling, and then some stuff in between. And this is complex, especially when you get interactions. But these peaks here, we can see, and those actually indicate then how much is full filling. So I can actually, at each location, measure what is the carrier filling, and that means at each location I can also measure the twist angle. So this is what we do. So this is in the photocurrent nanoscopy, different images. It looks like, oh, there's lots of stuff going on, but actually if you make now a line cut with versus doping, you actually see these very sharp lines here and here. Positive doping and negative doping, and that is the full filling. And then you can see slowly this changing, and that's basically slowly the twist angle is changing. This is quite nice. This is actually on samples that have shown superconductivity, so it's actually quite remarkable that this has been observed even in samples where the twist angle is varying. And then from this we can actually make a full map of the deduced twist angle in this sample. You can really see many different twist angles, including areas that are more homogeneous. Now, the last thing is that now I showed you this Seebeck profile as a function of filling that looked kind of smooth and boring with 1 peak. But it turned out we observed many more peaks. And this is something that's related to what people have seen initially in transport is that at each filling, so filling 1, 2, 3, and 4, they saw small peaks in the resistance. That's, of course, a global measurement. This was tri-layer graphene. And this has to do with different phase transitions. And this is related to polarizing the system in the valley and spin. And we actually see this also in the cryogenic near-field measurements. So that means we can now do this with spatial measurements. I showed you the image, but let me just show you a line trace. So the red curve is now the near-field photocurrent measured at one spot. And you can see a peak here, another peak here, another peak here. And these are direct measurements of the Seebeck coefficient. And in fact, what we also see is that it is strongly deviating from the classical mod formula, so the theory I showed you before. So the classical theory does not apply. So here you have to forget about our archive paper. And here actually we do see that there's a strong enhancement of the entropy. And entropy is actually a very important parameter to measure in these correlated systems. People have studied Pomerantchuk effect in magic angle graphene, which is related to the fact that you cool down the system and the entropy goes up. So it's kind of counterintuitive. And this is what we see, I think, in our near-field photocurrent measurements. Then we also have stuff on super moiré. When you have 3 layers aligned with HBN, we start to see stripes. I cannot explain. There's beautiful images. This is the end. Thank you. Chairman, make you stop.